here we will be looking at the applications of the differential elements that we discussed from the previous discussion. And the first one, for the differential length, the most common application of a differential length is the line integral. Line integral. There are two types of line integral. We have the scalar line integral, and we also have the vector line integral. In electromagnetism in EE126, we are more interested with the vector line integral. And to explain what it means of a vector line integral, so basically the most known example of a line integral is the energy or the work done from a given force when you are moving a certain body or a mass. So if you have a vector field of force that is going into that direction, then you have a mass somewhere here, and you want to move this mass into, if this is the point 1, you want to move this into this direction, this mass, point 2. And if this is a vector force, then if this is the path that you want to follow in moving that mass, then how much energy do you need to do that? And in physics, we know that the work done in doing that is just equal to the product of the force and the distance traveled. But in this case, because this is a vectorial in space, we usually use our differential length now, which we discussed in the previous discussion, because what we are doing is we are cutting this differential length or this length into very, very small differentials, and we calculate the work done at every differential. Then after that, we add them all through the curve or the path. So I will be using C here to denote that we are taking the integral into this path, C. It's the work done for a forced. Now, in electromagnetism, this is one common example, and we will be talking about this more later on when we go to electrostatic fields. Now, we have an electrostatic field. It's given by this uh, equation, E. So this is a field, and it represents x, y in the x direction, and we have x squared, y cubed, ay, and the unit is volt per meter. And this field is just in the xy direction because there's no z component of the field. Now, we want to determine the work done. If we want to move a charge q, which is 1 coulomb, following the path of a shape of a triangle whose vertices are 0, 0, 1, 0, and 1, 2 in a counterclockwise direction. So if we plot that, this is actually in xy plane because we only have x and y coordinates. So the path that we want, if this is the y-axis and this is the x-axis, is basically, so we start at 0, 0. Then we have another coordinate at 1, 0. So if this is 1, so let's say this is 1, 0. And we have another coordinate or point or vertex of the triangle at 1, 2. So 1, and you go up 1, 1, and 2. So if this is 1, 1, 2. Then we form a triangle. It's actually a right triangle. This is our path. So this will be our C. Now, we want to do this. We start at the origin and we go counterclockwise in that direction. So we have a field somewhere here in the xy plane, and we want to move our, if we have a charge here, positive q, we want to move that from following this path. And how much energy do we need to do that? And this is application of the differential length, so or the line integral. And to do that, we need to divide the basic way of doing this is we need to divide this solution by finding the energy into, because we have different directions. Let's call this one the first direction, and this one number 2 and number 3. So we need to divide it into 3 parts. And in electromagnetic field, I'll just give you the formula for the energy, but later on in our next chapters, we'll be deriving these formulas. But for now, because we're talking about the line integral application of differential lengths, I will just give you the formula for this. This is just equal to Q times the integral of the electrostatic field, the dot product of the electrostatic field, and the differential length. This is also a vector in a given path. So somewhat similar with the force and the mass and the displacement in in physics. So here we're given a Q which is equal to 1 coulomb. So we just remove that, and we have E equals to this one, x, y, ax, and x squared. Now, what will be our DL? Our DL is, this is now the differential length that we derived from our previous discussions. So we already derived this. And if you forgot the formula for DL, this is in XY coordinate or in rectangular coordinate system. So our DL in rectangular coordinate system is basically just dx in the x direction plus dy in the y direction plus dz in the z direction. But we don't have dz here, so we can just remove that dz because we are just in the xy plane. So our DL now will be just equal to dx ax plus dy ay. So this will change. It depends on the coordinate system that you will be using. So if you want to use the, for example, if the electrostatic field is not given in rectangular coordinate system, it's given in spherical coordinate system, or it's given in cylindrical coordinate system, then you know that the differential length will also change. But again, it's up to you to choose. If you want to convert, we have also discussed how to convert a vector field into the other coordinate systems. So if you're given a spherical coordinate system, but you forgot the formula for the differential length in the spherical coordinates, but you know the formula for DL, differential length in rectangular coordinate system, because this is just a simple dx ax dy ay, then you can convert that vector field into the rectangular coordinate system. Then you can apply again this solution. So there are so many ways to do that. Or if you don't want that, then you can just apply the differential length in the coordinate system of that vector. So let's continue this one. So the work now, first at path 1. So let's just call it the work 1, W1. So this will be equal to, using the formula, E. So our E, so this is the integral of that path. That E is just equal to x, y, ax plus x squared, y cubed, ay. And we take the dot product of the DL here. And the DL will be the DL that we will be using in that path. Actually, it's just in the x direction. This is just in the x axis. It's going through the positive ax. That's going through the positive ax. So there's no component for the y direction. So we can just take the dot product of this. Our DL here will be just equal to dx ax. We don't need to include dy ay because we're at this region of the path. So the component of that DL is just equal to ax. There's no y component. So that our limit now for the integral will just be also in terms of x. And that is from 0 up to this point, 0 to 1. Then we take the dot product, you can distribute that. Ax dot ax is equal to 1, ay dot ay is equal to 0. And we can calculate for the energy now. So this will be just equal to x times y times dx from 0 to 1. But again, what is y? What is y in this path. So this the equation of the line. If you look at this line here for the first path, that is our C, because we divided that into different parts. What's that equation? That's just equal to y equals 0. This path is just equal to y equals 0. That the equation of that line. So this means y is equal to 0. So if we substitute it here, y equals 0, then our integral now will be whatever the value here is, multiply that with 0, it always be equal to 0. So the energy that is used here in this path is just equal to 0. Then for the second path, let's call it W2. So this is the path going upward. Let's choose another color here. Let me choose green. So this will be the second path. And again, we need to determine the equation of that path, just like what we did in the first one. And this will be y will just be equal to what? There's no actually y here. This is just x equals 1, because this is a horizontal line. This is equal to x equals 1, horizontal to vertical line. So here, now in our integral, so this is, again, copy this one, x, y, our e. Just copy this. Or just copy the whole equation. Paste it here. Then what do we need to change here? We just need to change our x here, because we're just going upward here. We're going to the direction of y, positive direction of y, ay. So we don't have any component in the x-axis or the z-axis. So we can just say that this is dy ay. Then the limit will be also, because this is dy, so with respect to y, so our limit should be from 0 up to 2. So this should be from 0 to 2. Then we take the dot product, ax dot ay is 0, ay dot ay is 1, and we know that y, or x, we know that x is equal to, from here, x is equal to 1. So x is equal to 1. So we can just substitute that in our equation. So this will become from 0 to 2, and we don't have this dot product because it's 0. It's just equal to x squared times y cubed, x squared, or 1 squared times y cubed times dy. And 1 cube is just equal to 1. Then if you integrate this one, the integral of y cube, dy from 0 to 2. So this will be y to the fourth, 1/4, y to the fourth from 0 to 2. So you evaluate this, this should be equal 2 raised to 4, that's 16, then 0 minus 0, upper limit minus lower limit, divided by 4, 16 divided by 4 is just equal to 4. And the unit for this is joules for the work done. So this is the energy that we need to move the charge from this point to this point. Then for the third part, the last part, W2, 3. This should be equal to, let's copy this again. But this time, because if we look at our drawing, it's not equal 0 to 2. We need to include now both the x and the y direction, because we have a direction for y and direction for x. So here, this will be dx in the x direction plus dy in the y direction. So we need to include them both, and this will be the let's just call it C3, or the third path. And if we take the dot product of those two vectors, so we'll have xy times dx, xy times dx plus x squared y cubed times dy. And ay dot ay is 1, ax dot ax is 1. Then here we have dx and dy. So there's a problem. What should be our limit? So to do that, we need again to determine the equation of this line, just like what we did from the previous parts. So what will be this equation? So it's a straight line, and we can use 2-point form of a straight line. Given 2 points, we have 0, 0, and 1, 2. So we have 0, 0, 0, 0, and 1, 2. So what's the equation of the line connecting these 2 points? So we can let this one our x1, y1, this one x2, and y2. So using the 2-point form, so this will be y minus y1, where y1 is 0, and this is equal to the slope. The slope is y2 minus y1, so 2 minus 0 all over x2 minus x1, 1 minus 0. And you multiply this with x minus x1, which is 0. x1 is 0. So this is our 2-point form of a straight line. Then solve for the equation for y. So y now will be equal to 0. This is 0. 2 minus 0, 2 divided by 1 is 2 times x. 2 times 0 is 0. So this is just y equals 2x. So we know now that y is equal to 2x. So if y equals 2x, we also need to know what is dy, because there's a dy in our equation. So dy is this equal to the differential of this. So dy dx is actually equal to 2. Or dy is just 2 times dx. So now we know dy, we know y, so we can substitute them here so that our equation will now be just in terms of x. So this will be, so we have x, our y is 2x, so multiplied by 2x, then we have dx, plus x squared, you multiply it with y, which is 2x, then you cube that. Then you multiply dy, or dy is just 2 dx, so this will be 2 dx. So if you look at now our equation, we don't see y, we don't see dy. Then we can factor out that dx, and our limit now will be in the x coordinate, because we take the differential with respect to x. So our x will be from, we start here, our x here is 1, and we will go to 0. So this will be from 1 to 0. So from 1 to 0. Then let's simplify and factor out that dx. So this will be 1 to 0. 1 to 0. And we have x times 2x. This is 2x squared. And factor out that dx. Then plus 2 times 2, or 2 cubed. 2 times 2, 4 times 2, 12. Or 8 times 2. And this is 16. So this will be 16. Then x squared times x cubed, that will be x raised to 5. Then we factor out that dx. Then integrate this. So this will be equal to the integral of 2x squared, the integral of 16x squared. So 2x squared is just 2/3 x cubed, plus 16x is 16 over 6, 5 plus 1. X raised to 6, and this is from 1 to 0. Then the answer here, upper limit 0 minus, if they are all equal to 1, 6. So 2/3 plus 16 over 6, that's just equal to 10 over 3. But this is negative because it's 0 minus that one. So 10 over 3 joules. Now we know the work that is used from the different paths. So to determine the total or the net work that is used, W now will be just equal to the sum of the 3. 1, 2, plus 3. So yeah, if you add them, it will be W1 is 0, W2 is 4, this is 4, then you just subtract 10 over 3. And the answer will be just equal to 2/3 of joule. So this is how we compute for the work done here. we need to divide it into that different parts. There's another way in solving this, a simpler way in solving this without dividing it into the different parts. But usually we divide them to make it simpler, but the solution will become longer. Another way is the what we call the green theorem. So what do you mean? How do we use this theorem in solving this problem here? So basically, green theorem says, so if you have a vector f with x or 2, okay, let's just call it f of x ax plus f of z or y az plus f of z or ay, then f of z az. Then these components, these are all functions of x, y, z. So we can just, these are all functions of x, y, z. X, Y, Z. X, Y, Z. They're all functions of x, y, z. Now, to use the green theorem, so if we take the dot product, if we take the integral at a certain path of that vector and you dot that with that differential link in that path, then green theorem says that this is just equal to usually you don't have in the xy plane just like what we did that. This should be f f x ax fy ay. So this is just equal to the integral of the partial derivative of f of y with respect to x minus the partial derivative of f of x with respect to y. And you need to multiply this with the area, differential area. So in this case, this is ax and ay, so the differential area. So this is a differential area, or the absolute value, the magnitude of that differential area. So x and y, and that will be dx dy in that certain curve. Now, you apply this theorem to solve this problem. So let's try to solve this. Just copy this one using this theorem. So our f of x and f of y, or here in this case, this should be our f of x or ease of x, and this is our ease of y. So to use the theorem, the work done, because q is equal to 1, so we don't need to write that q. This is equal to 1. So this will be the integral in that path of the partial derivative of ease of x or y. This one, x. The partial derivative of x squared y cubed with respect to x, and we subtract it with the partial derivative of f of y or ease of y in this case, or ease of x, partial derivative of x times y with respect to y. And you multiply it with the differential area, and that's just dx dy. So this is a double integral because we have two differentials here. So we need to use double integration. Then the limit will be with respect to x and with respect to y. So now let's take the partial derivative of that first term, x squared plus y cubed. So if we take the partial derivative, the concept of partial derivative, if you don't remember, partial derivative is when it's the derivative with respect to x. So other variables in that, you treat them as constant. So for example, this one, x squared y cubed. We are taking the derivative with respect to x because partial of derivative with respect to x. Then we treat y cubed as a constant. So don't worry about that. It's not a product, the derivative of a product, but it's just a constant times x squared. So to do that, to take the derivative, that will be just equal to that constant y cubed, then the derivative of x squared. And that is 2x. So that's how we apply partial derivative if you forgot the concept of partial derivative. Here, Because this is with respect to y. So we treat x as our as a constant. So if you take the derivative of y, it's just equal to that constant. So for example, if you take 2x, what's the derivative of 2x with respect to x? It's just equal to 2. It's just equal to the coefficient. X here is just like the coefficient of x times y. So the answer is just equal to x. Because the derivative of y is just equal to 1. Then dx dy. Then what will be our limits? So we have limits here. For the x, the limits should be in the inequality. If we draw a region that is being bounded by the path, and that's actually the condition for a green theorem. You need to have a region that is being closed by that path. So this region can be represented by inequalities. What are those inequalities? For the x, it should be from 0 to 1, and for the y, it should be from 0 to 2x. So for the inequality, our x is from 0 up to 1. Then another inequality for the y. So we start at 0 and up to, we have 2x. Because that's the value of this region here. This is 2x. This equation is 2x. So our limit now will be based from this. So for the x, it's just equal to, it's from 0 up to 1. And for our y, it's just from 0 to 2x. Then we can now take the multiple integral. We can first take how do we do multiple integral calculus. So first, you need to choose what you want to first, the first one to take the integral. So in this case, we can just separate first the x, so 0 to 1. So this is our x, and we have dx here. Then we can first take the integral of the one inside. So this will be 2x times y cubed. 2x times y cubed minus x dy from 0 to 2x. So we just look at this first. Then afterwards, we go out from that. So what is that integral? So this will be equal to the integral from 0 to 1 dx. What's the integral of this one? So this will be, we have 2x y cubed minus x. We are integrating with respect to y, so we can treat our x to be a constant also here. So this will be the integral of y cubed. That is y to the fourth. Integral of y cubed is y to the fourth all over 4. Y to the fourth all over 4. Then this term, there's no y term here, so it will be just the integral of dy will be, and that's just equal to 1, or y times x. Here we have 2x times that. So the answer will be 2x times y to the fourth all over 4. That's the integral of y cubed. Here we have minus x, the integral of dy is just y. And we take the limit from 0 to 2x. So upper limit minus lower limit, the fundamental theorem of calculus. Upper limit minus lower limit. So this now will be equal to from 0 to 1. And this will be 2x over 4 is just equal to, you can just write this. This is 2. So 1/2 x. We have 1/2 x, or x over 2. X over 2. Then y to the fourth. The upper limit is 2x to the fourth. Then minus here x times the upper limit again. It's 2x. Then this whole thing, this is the upper limit. Then we subtract the lower limit. The lower limit will be, we just substitute 0 because that's our lower limit. So this will be x over 2 times y to the fourth. Our y now is 0 to the fourth minus x again times the value for y is 0. Then you multiply here with dx. And this will become 0 because any number multiplied by 0 is 0. You subtract it with 0, it's still equal to 0. And here we can simplify this in 2. We can cancel out that 2. But we have 2 cubed. So that will be 2 times 2 times 2. So that's 8. Then we have x to the 4th times x, then x to the 5. So this will be 8 x raised to 5. Then minus 0 to 1. This one is just equal to 2x squared. Then dx. So the last that we will be doing is we take the integral with respect to x. And to do that again, this will be equal to 8 over x raised to 5 plus 1 over 6 x raised to 6 minus 2. 2 plus 1 is 3 x 2 plus 1. Then again, upper limit minus lower limit 0 to 1. So our upper limit, so we substitute 1, that's our upper limit. So this will be 8 over 6 times 1 raised to 6. 1 raised to 6 minus 2 over 3 times 1 raised to 3. That's the upper limit. Then you subtract the lower limit. The lower limit, 8 over 6 times 0 raised to 6 minus 2/3 times 0 raised to 3. And this will be 0. So now our work done will be equal to 8 minus 2/3. 8 over 6 minus 2. And that will be equal to 8 over 6 minus 2/3. That's just equal to 2 over 3. Yeah, so it's the same answer here. We also have 2 over 3. But remember, when you use green theorem, the condition is it should be bounded. The area, there should be an area that is being bounded by the path. Or in other words, it should be a closed integral. It should be a closed line integral. So usually we put here a circle to denote that this is a closed integral. You cannot use this theorem if it's not a closed integral. So this is line integral.